and I couldn't. And between the suspension and the shake, what people refer to euphemistically as vibration, I wouldn't dream of riding it more than 100 miles at a stretch. You know, it's a complete fantasy. Across the country on one.
You get off like this. Well, what is it, a two-cylinder or what?
Two-cylinder, four-stroke, and 650 cc. Real fast. They're funny machines, you know. The British were real stupid when they, I don't know why they didn't seek to improve some of the more conspicuous shortcomings. I remember driving one day from Clinton up to New York and looking down, and the tampet cover on the top of the cylinder box there had vibrated loose, and it's spraying oil on my pants leg. A lot of that happened to a lot of people. In fact, I seen it in the magazine. Dear sirs, how can I keep the tampet covers on my Bonneville from coming loose? Well,
what do you do? You have to weld the bolts in or something?
They say use Loctite and kind of stuff. But
Tri-State Catalytic Club meeting. My name is John Stencil. We have a number of new attendees here that I haven't seen before, and I greet you. Welcome. Hope to see you again in the future meetings. Before we have our presentation, George Meitzner, I would like to have a short business meeting, a number of topics that we can briefly address, and then begin then with our presentation. Fred mentioned the March meeting that is going to be held in Cincinnati. The speaker is John Glees from Washington University. John was associated with the development of the CAP system. For those of you that don't know what this is a temporal analysis of product reactor design, primarily by John. And his presentation on the 15th in Cincinnati will be entitled Reaction Studies with Temporal Analysis of Product Reactors. I hope to see you there. Besides that March meeting, we will be having an annual spring symposium in Lexington on April 19th. The meeting place is at the Radisson Hotel, the same place that it was last year. Currently, we have 5 speakers lined up for that symposium, and we are asking our members if they know of someone they would like to hear, or if they would like to give a presentation, to either notify myself, Fred Tungate, or Vernon Aletka from Quantum. We have a variety of speakers, including some on NMR analysis, some on HDS, some on toll processing, on zeolite synthesis, and so it should be, from what I see, very good spring symposium. Young fellow up here in front. George received his bachelor's degree at the University of Wisconsin, subsequently went to Stanford. presentation of structured studies with EXAFS of heterogeneous catalysts.
Okay. Okay. That's the start. Up at the front. Okay, I would say structural studies with EXAFS of heterogeneous catalysts. My co-workers are Grayson Vaya and John Sinfeld, both of Exxon Corporate Research. Next, I would acknowledge too a couple of people, Farrell Lytle, Boeing Company, for assistance in the interpretation of results, and particularly in collection of data, and also Ken Drake, who is formerly a computer programmer with Exxon and now at Los Alamos. Next slide. All right, this is, can you see this, by the way? Okay. This is some material that some of you might be familiar with, just an introductory slide anyhow. The heading here says, supported metal catalysts present a mixture of phases. They're complicated things, as you know, consisting typically of a metal cluster, typically 10 to 1,000 atoms, which means something like 10 to 30 angstroms with in mean dimension. These little clusters are stabilized by the support. That's why you can make them so small. And they may contain more than one metal. Typically, the things that we like to look at contain more than one metal for reasons that I'll explain later. The support is, if anything, more complicated. The metals, my experience, the metals are more or less bulletproof. The supports are complicated things, and they're subject to all kinds of variability. These are typically refractory oxides or mixed oxides. They may be amorphous or crystalline or something in between. They are ordinarily doped or chemically modified in a manner which means that they're not ordinary crystalline alumina. The bottom line here is that many of the things that people use to study catalysts, the traditional tools, let's say, such as X-ray diffraction, don't tell the whole story because the order that you need to get maximum use from those kinds of tools just isn't present in the catalyst. Next slide, please. I'm going to talk about a process, reforming. I prefer probably you should keep this under your hat. Some of my management considers this a trade secret and don't want other people to know that we're involved in reforming at Exxon. But this is just, again, some introduction. Part of my point here is that I am talking about catalysts. I'm a little sensitive about this. It's a lot easier to mix noble metals with oxides and call them a catalyst than it is to demonstrate that they actually are such. So what I'll be talking about are platinum rhenium and platinum tin catalysts. Typical reforming reaction is the conversion of N-heptane with a octane number of 0 by definition at about 900 F and 400 psi over a catalyst to toluene, for example, with an octane number of 120. Highly desirable reaction. Next slide, please. Now, X-ray absorption spectroscopy, EXAFS, is a useful technique for studying catalysts for a number of reasons. These are, for example, that the X-rays are generally penetrating, so that the chemicals that are present on the catalyst under operating conditions don't interfere, neither do the supports, various matrix elements that are around. Windows that are necessary in order to reach high pressures, unaffected by temperature. EXAFS experiments using a beam from a synchrotron utilize a large-size probe, which averages across a macroscopic sample. That's not to say that you necessarily have a good sample from something that arrived in 90 hopper cars on a train, but the probe size is about 2 centimeters by 2 millimeters, for example. And this is certainly better than, say, an electron microscopist who is averaging across or is measuring on a field that's 10 nanometers in diameter. There are detection schemes for measuring X-ray absorption spectra that are suited to most experimental configurations. That is to say, the physical and mechanical properties of the sample aren't very important. The environment in which you contain the sample, the gases, the temperature, and so forth, don't really make much difference. You can find a way to set up a scheme for measuring X-ray absorption regardless of any of those conditions. I would call these last two items areas of diminishing weakness. One is that the number of sources available, the number of sources for the X-rays that you need is growing. They have long included Stanford Synchrotron Radiation Lab, and now PEP, the big synchrotron at Stanford. The National Synchrotron Light Source at Brookhaven. Now coming up under construction are the Advanced Light Source, which I think is at Berkeley, and the Advanced Photon Source, which is going to be at Argonne. There are other sources, Aladdin at Wisconsin and Chess at Cornell, other sources outside the U.S. And then, too, something that I think is kind of intriguing, there are new measurement techniques that also yield the same information as an X-ray absorption spectrum. For example, Raman inelastic scattering of X-rays contains X-ray absorption information. That's nice because you can use a monochromatic source to get a energy dispersed spectrum. Then there are such things as parallel eels, which use inelastically scattered electrons in an electron microscope to collect this information. And then, of course, someone has pointed out to me that in-house X-ray spectrometers are also improving so that you can do these kinds of measurements in your laboratory if you want to purchase a in-house source with a rotating anode. Next slide, please. This is a little dim, but it's just an introductory slide anyhow. What I have here is a typical EXAFS, X-ray absorption fine structure spectrum. By the way, EXAFS, EXAFS, stripped of all the superfluous words, is X-ray absorption spectroscopy. Actually, extended X-ray absorption fine structure spectroscopy, but it's really an X-ray absorption spectrum. Now, I've got such a spectrum over here. Probably it's hard to see. But all that's plotted is absorbance versus photon energy. It's like any other spectrum in that respect. Some photon energy here and some absorbance here. What we're looking at is absorption by rhodium, which I won't talk about any further in this presentation. This sharp increase in absorbance here occurs when the energy of the photons exceeds the binding energy of a core electron. For rhodium, this is a K edge, it's a 1s electron, and the binding energy is about 23,000 electron volts, quite high. Close to the absorption edge here, the energy that's absorbed by the core electron may not exceed the binding energy, but be very close to it, and then the electron gets trapped in some bound valence state. And so you might have some features close to the edge which are something like a map of the vacant valence level states. But out here, farther out in the spectrum, out to about 2,000 volts frequently, there's some oscillatory behavior. That's the EXAFS, the extended fine structure. And for reasons that are not really evident, if you think about them, what happens is an electron that's ejected from a core hole interacts with the environment of the atom that absorbed the photon in a manner that modulates the absorption coefficient itself. Think about what I'm saying. It's saying that the electron has absorbed a photon, it's gone out and interacted with the environment and modulated its own absorption coefficient. And it's quantum mechanical. But the modulation is basically a scattering pattern. And that being the case, then, the interpretation of this thing, which is really a scattering pattern, is fairly straightforward. So what do I have written here? Oh, so what we're looking at here is scattering of a photoelectron backscattered by the local environment of the absorbing atom. Next slide. This plot shows the applicability of these kinds of X-ray absorption experiments. This is a slide I got from someone else. What's plotted here is energy of the photons versus atomic number. And first of all, these hatch marks represent areas that are inaccessible in energy. Up here, above 30 keV, that's about a third of an angstrom, the energy of the photons is just getting too high, and they're either hard to work with or unavailable. I heard a speaker at the Materials Research Society, I think, talking about measuring absorption spectra of 1s electrons in the actinide elements. These are about 140 keV. He referred to these 25, 30 keV photons as sunshine and said you have to be a real man to work with 140 keV photons, which is, well, maybe that's true. I don't know. What I've plotted here is the binding energy of a K edge of a K electron, which is a 1s electron, versus atomic number. And as you go to higher atomic number, this binding energy increases. X-ray absorption spectrum can be collected using these electrons up to about 10. And at that point, the binding energy is really too high for practical purposes. Now down here at low energy, there's a gap. The VUV sources and soft X-ray sources furnish photons up to about 1,000 electron volts, and the X-ray sources furnish photons down to about 3,000 electron volts. And in between, there's a region that isn't really covered by any source. Unfortunately, that's where sodium, magnesium, aluminum, silicon, and phosphorus absorb. So those important elements are kind of hard to do these kinds of measurements with. We go up to higher energy. When we get beyond the energy where we can use a K edge, we drop down to the L edges. Those are 2s and 2p electron absorptions. Unfortunately, there's the L1, which is the 2s, and the L2 and L3, which are two different 2p excitations. And they're very close together, which means that for a while the spectra overlap and interfere with each other, and the interpretation is difficult. Then beyond the actinides, probably with hafnium out here or something like that, the separation of the L edges is sufficient that these kinds of spectra can be collected with L edges. So there's gaps because of sources, and there's gaps because of spectral interferences. But most elements are amenable to this technique. Next slide. This slide got a kind of an interesting Art Deco look due to a lot of image processing. It says a graduate student constructs a model of the universe, and this is a girl blowing up a balloon that says Earth on it. Now, we of course have to build a model too to interpret a spectrum. This actually is an Exxon researcher constructing a model of the world's petroleum reserves, and in the more sophisticated model this would be filled with petroleum. Our model is quite simple. Next slide. For interpretation of X-ray absorption spectra. It says here EXAFS measures the average local structure of each atom type. Here is a hypothetical bimetallic cluster. We've got black atoms and white atoms, of course. Now, we might collect the spectrum, an X-ray absorption spectrum, from the white atoms and another spectrum from the black type of atoms. They might be, for example, platinum atoms and rhenium atoms. Now, the EXAFS, given by this quantity here, from the white atoms is represented by a term due to absorption by the white atoms and scattering by the neighboring white atoms, and another term due to absorption by the white atoms and scattering by the black atoms. That is, we've got photoelectrons scattered by these atoms, and those different contributions add together to make the EXAFS. We also have a spectrum from the other kind of atoms, and the same thing is true. We've got absorption by atoms of type B, scattering by atoms of type A, and scattering by atoms of type B, so that the spectrum from this type of atom also is a sum of the terms. And then the whole spectrum is described by this relatively simple equation, which contains information on the interatomic distance, on the dispersion about the interatomic distance, and on the number of neighbors of this type. So that's the information that we can extract in principle. Next slide, please. Okay, one of the reasons, at least, that we like to work with systems that contain two interacting elements, not entirely scientifically guided. There's a practical reason, which has to do with how much information you can get. When you have spectra on two different types of elements which are interacting in the same sample, and then you can use a certain kind of information to interpret the two different spectra. For example, from the spectrum of A, I can get an AB distance. And from the spectrum of B, I can get an AB distance, and obviously those distances are the same. So when I analyze the spectra, I can force those quantities to be the same, and I'm effectively introducing new information to get a more reliable result. Similarly, the mean square relative displacement about the distance here, the mean relative displacement about this distance, determined from the A-type atom, and the displacement determined from the B-type atom, that also has to be equal because they're looking at the same bond. And finally, the coordination of atoms of type A by atoms of type B, it turns out, is equal to the coordination of atoms of type B by atoms of type A, subject to a factor which takes into account the atomic ratio of these two types of atoms in the sample. This last condition is equivalent to saying that if I have 6 neighbors, then 6 people also have me for a neighbor. So that when you take into account the number of different people we're talking about, we've got 1 here equals 1, or 6 here equals 6. So the value of this type of thing is that when we're analyzing 2 spectra, we're reducing the number of variables, and we're improving the information because we're putting in new information which is not model dependent. Next slide, please. This is a slide that describes the algorithm, really. And I like this slide because part of the point of this presentation is that this doesn't have to be 2 EXAFS spectra. Anytime you have a model for analysis of the spectrum, 2 different kinds of spectrum, if they contain the same parameter, then this kind of thing can be done with a computer. I'm talking now about a platinum spectrum and a rhenium spectrum. And I'm saying the platinum spectrum should be described with platinum scattering type atoms and rhenium scattering type atoms. And there's a number of platinum scattering type atoms, the platinum coordination number. There's a distance to platinum neighbors, and there's a dispersion about the distance. And then there's a number of rhenium neighbors, a distance to the rhenium neighbors, and a dispersion about the platinum-rhenium distance. The same things are true of the rhenium spectrum, all this information. Now look here, if I have 2 spectra, and I'm analyzing them to get all of these parameters, I've got a total at least of 12 variables for the 2 spectra. But it turns out you don't need all those variables because some of them are degenerate. The platinum-rhenium distance is equal to the rhenium-platinum distance because it's the same distance. The platinum-rhenium coordination number is equal to the rhenium-platinum coordination number if the atomic ratio is 1 to 1, which it is in the sample I'll be talking about. And this delta sigma squared, which is an adjustment on the mean square relative displacement about the distance, that is, it's something like a standard deviation in the distance, is equal whether it's determined from the platinum end or the rhenium end, and then you need a constant which comes into the analysis, but the constant is easy to determine, and it's not uncertain. So that when you analyze both of these spectra simultaneously, if they happen to be EXAFS spectra or if they happen to be some other kind of spectra, you can reduce the number of variables by 3. You've still got the same amount of 2 spectra, same amount of data, but you've got fewer adjustable parameters, which means you've got a better analysis effectively. Next slide. All right. I'm not going to talk about data collection. I'm not going to talk about data analysis anymore. I'm going to skip that part. The picture says you've got some equations up here. We've got some equations down here, and in between you've got then a miracle occurs. And the caption says, I think you should be more explicit here in step 2. But I'm not going to be more explicit. I'm going to skip all of that. Miracle occurs now. Next slide. And this is a description of the catalysts. Platinum rhenium and platinum tin, both reforming type catalysts. Neither of these, of course, are commercial catalysts. They're not proprietary materials. They're materials we made ourselves, but they do, at least to some extent, simulate the proprietary ones fairly closely. Platinum rhenium on alumina prepared by co-impregnation and reduced at 775 Kelvin. There's a typo here. This is 1% platinum and 1% rhenium, so the atomic ratio is 1 to 1. Then we have platinum tin on silica, definitely not a commercial type of material. We put silica here because it's not interacting and maybe simplifies the treatment of the metals. Co-impregnation, calcined at 795 Kelvin and reduced at 775, and 1% platinum and 0.6% tin. So this is also 1 to 1 atomic ratio. And then finally, this material, which is quite realistic commercial type catalyst. It's platinum tin on alumina, prepared by co-gel method, which means co-precipitation of tin and aluminum hydroxide probably, and then calcination of the gel, following the recipe provided by Rausch, UOP patent issued in '73. And it's 1% platinum and 1.2% tin. This kind of prep is designed to put the tin inside the alumina. You see, you co-precipitate them and then you calcine, you get a mixed oxide. Next slide. Okay. Oh, it's 1% rhenium. Yeah, this is a mistake here. That's wrong. All right. Moving on to results. We had previously, before the work that I'm describing here really, recognized that when you have spectra from two different components in a sample, you can reduce the number of variables by recognizing that there's a equivalence in the meaning of the parameters. For example, the platinum-rhenium distance is equal to the rhenium-platinum distance by necessity. What I've plotted here is distance in angstroms between platinum and rhenium, and a dummy parameter that we use to adjust the platinum-rhenium and rhenium-platinum distance from an analysis. We would repeat an analysis adjusting this dummy parameter until we'd forced the rhenium-platinum distance to equal the platinum-rhenium distance. Some other variables that we were also able to determine, such as the composition of the rhenium coordination shell, first rhenium coordination shell, were mildly dependent on this parameter down here. But we used this criterion that the REPT distance equal to PTRE distance to fix any other physical parameters that we determined. So this gave us the platinum-rhenium distance. It was here 2.63 or something like that. And it also fixed the composition of the platinum and rhenium coordination shells. Now this was a good thing to do. There are other variables that we could have fixed as well, but for practical purposes, this was an enormous amount of work already. And if you try to put constraints on other variables as well, the amount of work increases so rapidly that soon you just can't cope with it. So this was the only such criterion we formerly enforced. Next slide, please. Now, these are structural parameters from analysis of EXAFS. Happen to be coordination numbers. Atom pair over here in a platinum-rhenium catalyst. The atom pairs are PT-PT, PT-RE, RE-PT, and RE-RE. In a previous analysis where the interatomic distance was fixed as I've described, determining these various coordination numbers, I say couldn't determine them because the coordination numbers were correlated with another adjustable parameter, and the correlation was so strong that it just was indeterminate. We artificially reduced the number of variables by determining composition of coordination shell, and we found that platinum has 65% platinum neighbors and rhenium has 44% platinum neighbors. Pretty well mixed. In our present analysis, we have fewer adjustable parameters, and consequently the correlations are not as strong. There are not as many variables. And this is what we find, that platinum has 5 platinum neighbors, rhenium platinum and platinum rhenium neighbors are about 3, and rhenium has about 4 rhenium neighbors. The compositions of the first coordination shell that you calculate from these are the same as what we determined previously, however. So what we get here is that the total number of metal neighbors about platinum is around 8. Total number of metal neighbors around rhenium is about 7. That would tell you that you've got cluster sizes 10 to 20 angstroms perhaps, and rhenium is occurring preferentially in the little lower coordinate sites. Next slide. Now, one of the interesting things, this is a fitting exercise. We get our parameters by a nonlinear regression. And so previously we had, for analyzing two spectra, we had 12 adjustable parameters, 13 really. And our calculated spectrum versus our actual data looked like this. It's a damn good fit. This is a fit to the platinum spectrum. This is a fit to the rhenium spectrum. Now, in our present work, we had, instead of 13, we had 9 adjustable parameters for analyzing both spectra simultaneously. It's not a coincidence that the fits are just as good as they were previously. That's because, as I said, some of the variables were degenerate. So what we've shown is that using a smaller number of variables, you get more data out of the system, and you get equally good, qualitatively, you get equally good fits. Next slide. Okay, platinum tin catalysts. I say EXAFS structural parameters for platinum tin catalysts. Two different types of samples. One, platinum tin on silica. This is hardly a catalyst, in fact. If you try to use it for a catalyst, it doesn't work very well. It's 1% platinum and 0.6% tin on silica. The other is this platinum tin alumina catalyst. This really is a catalyst. It's 1% platinum, 1% tin on alumina. The tin is really incorporated into the alumina matrix. We're looking at the platinum tin atom pairs in both cases. The number of tin neighbors of a platinum or a tin atom is about 6 in the platinum tin on silica system, and is about 1/2 in the platinum tin alumina system. That is to say, platinum has a fairly tin-rich environment. Tin has a fairly platinum-rich environment. Both of these things have metallic environments. In the case of the alumina-supported system, they're not seeing very much of each other. The interatomic distances are informative, platinum tin interatomic distance. On silica-supported system, it's about 2.77 angstroms. Well, in the intermetallic, various intermetallic compounds formed by platinum and tin, the platinum tin distances are in the range of about 2.7 to 2.8 angstroms, which includes this distance. And in fact, platinum and tin on silica form intermetallics. The tin gets reduced to tin metal, and it reacts quite exothermically with platinum, and you get ordered solid solutions of platinum and tin. That's why we see this metal-rich environment for both, and that's why we see this particular distance for platinum and tin. Now, on alumina, we get something else. We get this very short platinum tin distance. And by the way, this is a small number, but it's not indispensable. It's a real number. We get this 2.6 angstrom platinum tin distance. Well, where does that occur? There's a number of coordination complexes where platinum has a SNCl3 ligands. And in those various complexes, you see platinum tin distances in the range of 2.45 to 2.6 angstroms. So whereas platinum doesn't see very many tin atoms in here, those that it does see are at a short distance, characteristic of this kind of covalent bonding. Next slide, please.
Just a quick
Yeah.
clarification. You said something about the reactivity of these catalysts. Are you saying genericity of those compositions, or do you mean specifically that these preparations were tested?
You mean the catalytic activity.
Pardon?
The catalytic activity.
Of these particular
Yeah.
samples, or generically those
well,
preparations?
Either one. Platinum tin alumina is a commercially used reforming catalyst. It's a commercial. Ours did not necessarily reflect the composition of the commercial catalyst, but this was prepared according to a patented route, and it's likely that the patent we followed is approximately the procedure that's used to make the commercial reforming catalyst.
But you did not test the activity of these.
This specific prep? No, not for reforming. This one over here doesn't follow any known commercial prep, and for those things for which we did check its catalytic activity is very poor. Okay, we look at SNO atom pair, the oxygen neighborhood, the neighborhood of tin looking for oxygen in these two samples. We find that in this sample, the silica supported, where there's a lot of platinum atoms in the neighborhood of tin, there's very few oxygen atoms in the neighborhood of tin. In this sample, where there are very few platinum atoms in the neighborhood of tin, there's quite a lot of oxygen in that neighborhood. Well, what are we saying here? we're saying that in the silica-supported sample, the tin has gotten reduced and formed intermetallics with platinum. And in the alumina-supported sample, the tin has resisted reduction, and it has a more or less acidic environment. Next slide, please. This one is, there's probably no hope for this slide. Locked wheels, yeah. I would say we should dispense with it. That's what I'm afraid of. That's far enough. I'll tell you what's on it. We're looking at the position of the absorption edge. Since we're exciting core electrons, we're actually measuring a binding energy. And the more you oxidize the absorbing atom, the more you increase the binding energy in general, for reasons that make sense, good electrostatic attraction. So we're looking at the binding energy of tin in various catalysts compared to the binding energy of tin in a foil for its 1s electrons. Now, over here, see, this is in electron volts, -1 up to +7 electron volts. +7 means it's shifted to a higher binding energy. Over here are some tin-4 compounds, SnCl4 and SnO2. They have a higher binding energy than tin in the foil, which is not unexpected. That's tin-4. In the middle, we've got some tin-2 compounds, PTSN2, a trans salt, cis salt, SnCl2, tin oxalate, SnCl2 hydrate. They're down around 0. It turns out we can't discriminate between tin-2 and tin metal. The binding energy doesn't change for one reason or another. And here we've got tin in various catalysts. Tin alumina, tin silica, tin platinum silica, and tin platinum alumina. These all have near 0 shift in binding energy. The conclusion then is that in these catalysts, the binding energy of the tin is either comparable to that of tin-0 or tin-2, but this is definitely not tin-4 in the catalysts. Now what we've seen is that tin on silica with platinum has a metallic environment, so we say it's tin metal, and it's formed intermetallics. Tin on alumina has a lot of oxygen in its environment, so we say it's probably tin-2. It has the tin with platinum on alumina has a short platinum-tin bond as well, so we say there's probably an anchoring site, which is a sort of a bonding interaction between platinum and tin on those supports, on alumina. Next slide. Okay, I'm about done here. I'll summarize. Okay, what we've got here is a couple of scientists standing at the board. This guy's written out an equation, and he's gotten to the equal sign, and he's saying, this is the part I always hate. So the next slide. All right. Concerning platinum tin catalysts, which I think are the more interesting of the lot. This is a sort of a coarse model for the interaction that I am claiming goes on in those types of catalysts. There is unambiguously an interaction between platinum and tin, and the tin is substantially 2+, not tin-0. They're not really bimetallic catalysts at all. They're platinum on a modified support. What I've shown here is is just some structures. These are platinum-tin coordination complexes. We've got a platinum atom at the center in both cases. Over here we've got SnCl3 ligands out here, and chloride ligands out here, and there's got to be 2 cations around. And over here we've got this interesting trigonal bipyramidal platinum-tin-5 complex. It's got platinum at the center and 5 of these SnCl3 ligands out around the perimeter. These things are simple to make. If you mix stannous chloride and hexachloroplatinic acid, you'll end up with these things. They're easy to crystallize and do X-ray diffraction on or anything you like. But they have got this short platinum-tin bond, which is well characterized. That's the kind of bond we see in our catalysts, and tin-2 is the kind of tin we see in our catalysts. Next slide. finally, concerning platinum rhenium and platinum tin catalysts. My first point is that simultaneous analysis of multiple spectra increases your confidence in the parameters that you extract from the spectra. Now, I don't think it's appreciated that it is possible when you have two different kinds of spectra, say NMR spectra and infrared spectra. If there's a model that describes the data in those spectra, then it's possible to use them simultaneously and force agreement between them in a manner which tends to cancel the systematic errors in both models. If you do an analysis of the spectra with a computer, the computer can insist that the distance or the coordination number you extract from one is equal to the distance or the coordination number you extract from the other. And one of them has one kind of error, another has another kind of error, but the kinds of errors are probably different. And you get some improved confidence. Now, when there are two of the same kinds of spectra, then all you do is reduce the standard deviation in the value of the parameter. Statistically, you get a better number. All right. Rhenium in our catalyst that I've described here was first reduced, and second was interacting strongly with platinum. There was a lot of platinum-rhenium interaction. That was, I would say, a true bimetallic catalyst, and these were well-mixed clusters. Alumina interferes with the reduction of tin-2, and silica does not. This I would call a true example of a strong metal support interaction, and one that's significant in the area of catalysis, as opposed to another kind which certainly happens, but is hard to demonstrate a use for. And finally, tin-2 forms bonds with platinum-0, whereas tin-0 forms intermetallic compounds. And incidentally, tin-0 also coats the surface of the platinum and renders it unavailable for catalytic reactions. Thanks.
There's time for discussion, questions. Go ahead.
Okay, George, I was interested in your comparison of your platinum 2 catalyst with platinum tin organometallic. In those compounds, platinum is 2+. In your catalyst, when you're doing the EXAFS, did you see, some people claim that the strong interaction of platinum with the support yields a platinum partially positive. Now, did you see any evidence of this in your EXAFS work?
If it's a little bit positive, it's very little. Something like a tenth of an electron deficient or something at maximum.
Okay, so you're seeing
we don't
metallic platinum.
we would say metallic platinum. Yeah.
How do you visualize platinum being 0 and the SNCl3 being minus?
Well, of course, first of all, it's not in the catalyst. It's not SNCl3. It's more like SNO. But yeah, well, I don't know. I don't know how much work has been done on those kinds of interactions. I suspect that they're much more common than is appreciated. Certainly, there are inorganic complexes which have a nominally zero-valent metal center, and so those kinds of things are not without precedent. This is somewhat unusual. You just don't see atomic zero-valent platinum around, and so you can hardly determine whether such an interaction will occur in other systems. We're making the proposal entirely on the observation that platinum has neighbors which are much closer than they ought to be.
Can you, from selective time absorption, can you determine the oxidation state of the tin in there, or is there any method you can?
Yeah, I don't guess I can discuss it though.
Well, the other question is that tin oxide separate phase than aluminum, or is it really replacing the proton and the aluminum?
We can't see by any X-ray diffraction, for example, a phase that we can identify with the tin. The alumina looks exactly the same with and without the tin, and so we don't identify any phase with it. I suspect that the best description that could be offered right now is that it's something like dispersed tin oxide. But as I say, alumina traps tin and silica does not, so it is a distinctive interaction.
That's another one. I was just kind of curious. A lot of people are doing work with organic metallics, trying to deposit them on the surface, and that's an obvious extension of what you're doing. Try any mixed carbonyls, platinum rhenium, mixed carbonyls, or any kind of platinum tin organic metallics.
The platinum rhenium, no, that's not too active synthetic area. Platinum rhenium catalyst has been used in reforming for decades, and I don't know how much farther a person could take that. Platinum tin, on the other hand, we haven't done too much with that, but there has been quite a lot of work using those complexes, for example, to prepare catalysts. What you find in general is that if you encourage the interaction between platinum and tin before you deposit the tin on the support, you also encourage the reduction of the tin, which is apparently detrimental. So that, on the other hand, if you do a co-impregnation with platinum and tin, you get these complexes. The catalysts are actually made by putting down the tin first, at least as taught in the patents. Putting down the tin first, either the way I said, precipitating from a solution of aluminum chloride and tin chloride, and then calcining the precipitate, or by adding tin and then calcining the daylights out of it, and then adding the platinum afterwards. Then you don't reduce much tin.
Good. No, go ahead, John.
Could you give a summary, speculative summary on what does the tin do for the overall catalyst structure that gives the reforming activity higher than you would have without it?
Well, it's kind of an interesting question. So the catalyst, the platinum tin catalyst, is operated in a radically different manner than a platinum rhenium or platinum iridium or platinum only reforming catalyst. It, in fact, does not perform particularly well, I would say, when it's operated the same way. Platinum tin catalyst, as described by UOP and by the procedure that they sell, is on a belt, and it's continuously passing through the reactor, and then it's being regenerated on a very short cycle time, very short cycle length, and then put back into the reactor. And it's being operated under what you would call very severe conditions, which is very low pressure. So you've got conditions that really promote the formation of coke, but you're regenerating it so rapidly that it doesn't have time to die. Now, if you try to operate a conventional reforming catalyst that way, it doesn't work because you can't regenerate it continuously like that. If you put a platinum tin catalyst into a conventional reactor, it doesn't work very good either, for reasons that I don't know what they are. So it's not really clear that the difference between the two catalysts isn't in the regenerability or something like that. However, with that said, tin does probably function as a dispersant or something like that of platinum. Keeps it from agglomerating, perhaps, which is also consistent with a hypothesis that the real benefit of platinum tin catalyst is in its regenerability under the conditions that it's used.
Have you tried any other bases like zirconia or titanium?
No, a lot of work that a person can do. A lot of work.
First, clarifying question again, is the catalyst sample that you took, which you specially prepared, was that on a powder or single crystal or what? Or
No.
I wasn't sure. You know, maybe you clarified it. I didn't get it.
The catalysts that were described here, platinum rhenium was prepared by starting with an Ada alumina, Ada alumina because we've always used it.
Sure.
Wetting it with an aqueous solution of hexachlorophenic acid and purinic acid. Drying that,
Yeah.
I guess calcining at about 600 Kelvin. That was calcined under pretty mild
Sure.
conditions. And then reducing at 725 Kelvin. Finally fascinating. Re-reduced before we did the spectroscopy. The platinum tin catalyst was prepared by making an aqueous solution of aluminum chloride and stannous chloride, precipitating with hexamethylene tetramine, and that makes a gel. We actually incubated the gel for a while and then centrifuged it to get something that we could calcine. And that also resulted in a powder.
So you're looking at powders only?
Yeah, powders.
Powders, spread them out.
Certainly not single crystals or anything like that. Now these are all things that, particularly the platinum tin, I would insist that if you put that into a conventional reformer, you get something that looks like a conventional reforming catalyst.
Now to the main question. Once you have these as powders and you're looking at a wider area, which you said is a strength, is looking at a larger area, how are you really sure that the structures that you're proposing indeed do exist? Have you run any standards to confirm that those, you know, the analysis that you did due to either Fourier transform or whatever are indeed kosher? And could you give me a little warm feeling for the whole procedure?
Not usually I give you a warm feeling. One thing about EXAFS, now we just regard it as another way of getting information about catalysts anyhow, but one thing about it is you work on systems where ordinarily you can't get any information any other way. Inherently, you're uncheckable. However, the platinum tin did unambiguously make intermetallic compounds. You could see them by diffraction if we needed them well enough or something like that. You could get an X-ray diffraction pattern, which is characteristic. Platinum on alumina, no, we can't check that result. We can show that we can identify such a complex if it's present by doing the same experiment on well-characterized PTSN5, for example, that trigonal bipyramidal complex. We can see that. But as far as the structure that I proposed for the platinum alumina catalyst, I don't think you'll even find another way that can observe it, much less give you precise information about it. So it remains a hypothesis.
Well, I was thinking of another way might be maybe not to your lower crystallite sizes, but the larger ones by analytical electron microscopy, because you are dealing with fairly large concentration of both materials.
You can see with electron microscopy, you can certainly see spots which are platinum. And what you see if you try to do the fluorescence measurements is that you've got tin all over the place. But you can't make a spot, you can't do an analysis on a spot size which is comparable to the size of the metal clusters that occur in these catalysts. So that you don't...
Not even with the latest AEMs?
Very, very small clusters in there, very small. In fact, visualizing them is already about all you can do. And I think you have to have a microscopist's imagination to have confidence there.
All right, one final one. How deep is the EXAFS structure modified by the atoms that are subsurface?
Oh, this is a transmission measurement. It's measuring right through a macroscopic thickness of sample.
Right.
There's no direction, in the experiment that we perform, there's no directional specificity. It gives you exactly the same information of all the different orientations. Just averaged around 360 degrees.
Over the whole thing?
Over the whole thing, yeah.
So,
Averaged over all the atoms, over all the environment of the three atoms.
so any structure you propose, whether it's on the surface or subsurface, all the same? Or any mixture thereof?
That's right.
Heterogeneity?
That's right. I'm beginning to believe, though, from what I see about catalysts, that they're, they may be somewhat less heterogeneous than people assume. People assume they're heterogeneous because you don't apply strict controls, but in the field of unsupported metal clusters, where people are evaporating metals into a gas phase and then doing mass spectral analysis, we're seeing that there are stable sizes, for example. And there may be driving force that gives you a somewhat more uniform distribution of cluster sizes and shapes than you expect to find. I just throw that out as my personal feeling.
Care to comment on the centering mechanism and how you can observe whether time axis or redispersion to generate these time gaps?
Oh, redispersion, certainly redispersion would be easy for us to observe just because the coordination number is extremely sensitive parameter when the particle size is below about 20 angstroms. You go from a coordination number of 0 for a 3 angstrom hypothetical cluster to a coordination number of about 10 for a 20 angstrom cluster. That's in a range where chemisorption is insensitive. You see other things as well. You see the formation of compounds. You can watch the chemistry go on. For example, if you treat with chlorine and you get a metal chloride, this metal chloride might be in units of 1 molecular unit. You can't possibly see it with diffraction or something like that, but you can identify it in a very simple way and straightforward way with this measurement. You see, you can fingerprint it, nothing else. So there's two ways really you can study redispersion here. One is you can get a good sensitive indication of particle size, something about particle morphology, and the other is you can study the intermediate chemistry and see what kind of chemistry you're going through and so forth.
What if you don't have a synchrotron Meitzner?
No. Yeah. The only reason a person would ever put up with the trauma associated with making these measurements is because it's so hard to get information on these kinds of materials, and you're happy for what you can get. Exxon has currently got 5 beam lines which are ostensibly operational and 2 more under construction, and we really can't do a single measurement right now. It takes a lot of patience. It's not something that you can commit yourself to do next week. It really is a powerful technique, great information when you can get it, but you got to have a sideline.
One final hypothetical question. What if I did not have any other analytical techniques available and I gave you a sample to look at it with EXAFS? Would you be able to come up with a definitive structure of the type that you showed us today?
No,
How much are you relying on other
ordinarily,
information?
no. In this case, that structure that I showed you today is, those structures that I showed are diffraction structures of, compounds. Mm-hmm. And my basis for proposing them here is just 2 pieces of information. One, that there's a platinum tin contact at all, and the other that it's short, so it's got a bond length in that range. You can't, with this kind of measurement, which has not got any angular dependence, you can't propose a 3-dimensional structure. Mm-hmm. There just is no basis for it. Mm-hmm. The beauty, of course, is that at least the current thinking is the catalysts don't really have those kinds of structures in them. And that's also the limiting factor for most other